Good morning. We had been talking about sensing mechanisms in the last class. We had already looked at how to sense speed. So in yesterday's class, we talked about three types of speed sensing mechanism. One was using a tacho or tacho generator. And the second one that we talked about was an encoder. And the third one was a resolver. So we said that encoder and resolver are completely digitally compatible, whereas a tacho generator definitely is an accurate arrangement which is going to have a voltage, DC voltage output as per the speed. However, that voltage has to be converted into digital. So analog to digital conversion becomes necessary. Without analog to digital converter, this will not work. So this is what we were talking about in the last class. So in the last class itself, I was telling that in today's class, we will be looking at voltage and current sensing, as well as torque sensing. Actually, torque sensing is very commonly not used in many of the systems. That is because the torque sensing generally is a little bit more cumbersome and it is also very expensive. So torque sensing mechanisms generally use strain gauges. So this has to be fitted on the shaft itself, and in the field, it's going to be very, very difficult to access the shaft of the motor and fit in the strain gauge right there. So it's not going to be easy to fit in this in field applications. So that's one reason why this is hardly ever used. Rather than that, what we tend to do is to compute the torque. So if we are able to sense what is the current, and if we know the flux, then we should be able to compute the torque, which is a product of current and flux and some of the motor constants. So using that, we should be able to get the torque. So in most of the cases, we don't use torque sensors. Rather, we compute the torque. This is what is done. So let us first now try to look at voltage and current sensing. So current sensing is the one which is very commonly done in many of the drive system. So current sensing, the easiest way to sense current is to use a current transformer. So a current transformer can be used generally to sense an AC current. A current transformer is exactly like a normal transformer. Only thing is what we are going to have is, if let us say this is the conductor in which I want to sense the current. So this is the main conductor through which the current is flowing. Okay, this capital I indicates the RMS current value. Let us say this is the RMS current that is flowing. Now, if I have a large number of turns that is surrounding this. This is the secondary of the current transformer. The primary happens to be the main conductor itself. So the main conductor itself will act like the primary of the current transformer. So this is going to be the primary of CT. And the secondary will have a large number of turns with thin wire. This is going to be really thin wire. So this is going to be the secondary. So this secondary, what is there, will be connected to a resistance. The resistance will be connected right across this secondary, and this is going to really give an output voltage. So if I try to measure what is the voltage across this resistance, this voltage is going to be my output, which would be proportional to the input current RMS value. So how this works is, if I say that primary by secondary turns ratio, if I try to look at it, the primary is just one conductor, so I have to write this as 1, whereas the secondary might have n number of turns, so this is going to be 1 divided by n. So this will be equal to I secondary divided by I RMS, which is the primary. So the current ratios are inversely related to the turns ratio. So I am going to have the secondary current, what I have got, is going to be equal to IRMS divided by N. So this N is going to be a real large number, because of which even if I have to measure, for example, 1000 ampere of current, and if I'm going to have N as 1000 turns, then I'll get only 1 ampere as the secondary current. So the secondary current, what is flowing here, this is going to be only having 1 ampere. So if I assume that I'm going to connect a 5 ohm resistance, for example, I'll still get only 5 volts as, so 5 volts multiplied by 1 ampere will give me only 5 volts as V out. So this can definitely be passed on to an electronic circuit without any difficulty. Only problem normally we face with the current transformer is because this wire generally is not wound this way to have a coupling which should be good. So what we generally have will be a toroidal core. So a toroidal core is somewhat like this. This is like a bangle. So it is going to be made up of iron, and it will be made up of multiple layers of thin lamination. And around this winding is going to be wound. So I'm going to have the winding wound around like this, like this. So I'm going to have the winding wound around this. And this is going to go around like this completely. So a large number of turns will be wound. And from here, I'm going to have one end protruding out, and from here, another end protruding out. So now the main conductor will be passed through this itself. So the main conductor, so I can imagine as though if this is the main conductor, around that I'm going to have this toroidal core. It is like a bangle which is through which the wire is passing. So this is the main conductor, and this is the toroid. And around this, I'm going to have the wire which is wound, and this is the secondary. Now, at the end of this, I'm going to connect the resistance. So this is the way the entire CT is going to be. So this core generally will be a ferromagnetic core. And because it is ferromagnetic core, I will have the problem of hysteresis as well as saturation. Both are going to exist, which means there will be non-linearity in the measurement when the current is either too low or too high. In either condition, I am going to have definitely non-linearity creeping in when I am looking at how I am getting the secondary current or V out with respect to the primary current. If I try to look at what is the primary current or IRMS that I am passing through the winding, it may not have linearity initially because of hysteresis, and it will not have linearity again finally because of saturation. So I will not have linear relationship between the input current and the secondary current or output voltage at very low current values as well as very high current values. So the range has to be specified very clearly for how long the current transformer can work. So this is one problem that could creep up with the current transformer. Otherwise, if you look at the current transformer, it's a very, very simple arrangement because it's just a transformer in action, and the transformers are characterized always by very high efficiency. So you will hardly see any losses. This is one of the major advantages of using current transformer. And another thing is, so current transformer, one problem could be non-linearity. So one problem could be non-linearity. And another problem that can crop up is it can work only for AC currents. It cannot work for DC currents because transformer will work only for AC current. It cannot work for DC current. So you are definitely going to see that it is useless in the case of cannot work for AC current, DC current. So it can work only for AC. This is another thing. And the third thing is, if you look at the turns ratio, we already said that I secondary divided by I primary or I RMS is going to be 1 divided by N. So by chance, if the current transformer is open circuited, if CT is open circuited on the secondary side, then we are going to have the voltage ratio also being valid. We are going to have this to be whatever is the V primary divided by V secondary. So if you look at it, the primary circuit, if it is carrying something like 230 volts, the secondary side voltage is going to be N times 230 volts. So this will be enormously high. By chance, if I open circuit the current transformer, this is going to be extremely detrimental to the health of the current transformer itself because this insulation will rupture. Very, very high voltage will be induced on the secondary. So we have to ensure that never, ever the current transformer secondary is open circuited. So what we connect as the resistance across the current transformer should be really, really a small resistance. What do we mean by the small resistance? It depends upon whatever is the R equivalent of the current transformer, what we can find out by conducting open circuit test and short circuit test. So R equivalent, whatever we find out, compared to that, I should connect the transformer resistance, what I am connecting across the transformer, it should be smaller. So this R equivalent has to be much greater than the resistance connected across the current transformer. So if you look at the current transformer, the advantages, so I said that these are the disadvantages or demerits. So one is non-linearity, the second one is it can be used only for AC current, and the third one is by chance if I open circuit the secondary, then very high voltage is going to be induced. These are the problems with current transformer. But the advantages of the current transformer are, one of the thing is it's going to be a very simple arrangement. It's not going to take much longer to install a current transformer in any system. Even for thousands of amperes of current, I will be able to find a good current transformer which can measure the current with fairly good accuracy. Second advantage is that I'm going to have isolation. So isolation is always present between the current, the high power circuit and measurement circuit and measuring circuit, because transformer itself will always have isolation. So I don't have to make any extra arrangement for providing isolation. Now, if I use this, sometimes I might like to have the average value after rectification. So sometimes what we will do is, let us say this is the primary where I want to measure the IRMS. So I will have the current transformer output from here. And this is the resistance I have connected across the current transformer. This will be pushed to a rectifier. So maybe I can just use a simple diode rectifier. So I can use a simple diode rectifier from here. So this will be connected to the rectifier like this. At the output of the rectifier, I can actually connect an ADC, analog to digital converter. And if I want, I can put a capacitor so that I'm going to have filtering out the oscillation. So this capacitor will filter out the oscillation, and whatever is the output, this can be given to an ADC. After maybe a filter, if you want to put a filter external, that also can be done. And this can be given to an ADC. So this can be converted into a digital value. Another way is sometimes we might like to exactly have the instantaneous value, in which case we will have this as the current transformer and this is the main conductor. So this is the CT. So now from here, I'm going to take out the output and I can put a resistance again. I have to put a resistance, and the output of this I can directly take to a level shifter. This we talked about earlier itself, because we said that some of the ADCs will not be able to take the negative value directly. So if I am going to have this as my current transformer output, I might like to add, let us say the peak is plus 2.5 and the lower peak is minus 2.5. So I can add with this a 2.5 volts level. So I'm going to shift it by 2.5 volts, in which case I can draw this as, it will start like this at 2.5 volts and it will go through the negative side and something like this. So this is going to be 5 volts and this is going to be 0 volts when I add plus 2.5 to all these waveforms. Okay, the entire waveform. So the level shifter will ensure whatever here it is plus 2.5 to minus 2.5. That is going to be the way the voltage is changing. Whereas here, this is going to be 0 to 5 volts. Now, this can be passed on to an ADC directly, or this can be passed on to a sample and hold circuit. So what a sample and hold circuit will do is, it will sample a particular value at a particular instant. Then it is going to hold it for a little while. Then it is going to sample it again after a few milliseconds. Then it is going to hold it at that particular value. So this held value can be passed on to the ADC. So you are going to essentially sample the value every 2 millisecond or 3 millisecond, and then this will be passed on to the ADC. And one more thing we will do before we pass on to the ADC is to generally put a diode at a particular, direction. So if there is any negative voltage by chance that is coming up, this diode will conduct and eliminate those negative values. This is one thing. And one more thing that we might like to do is to put a Zener diode again, which will ensure that the voltage at this point does not go beyond whatever the ADC can handle. If the ADC can handle only 3.3 volts plus 3.3 volts, nothing more than that, we might like to put a Zener diode which will break down for any voltage greater than 3.3 volts or 3.2 volts. So we might have a Zener of 3.2 volts rating. If we are going to say plus 5 volts is the maximum limit that can be handled by the ADC, then we might like to put a Zener diode of 4.7 volts rating so that anything more than 5 volts will be completely clipped by this particular Zener diode. It will break down and it will allow the current to pass. So putting a diode and a Zener diode will ensure that no negative voltage goes. So no negative voltage and no positive voltage greater than V Zener breakdown value. So ADC will get no negative voltage and it will not get positive voltages greater than breakdown voltage of the Zener. So this is the way we normally connect it to the ADC so that the ADC will be protected irrespective of whatever is the voltage that is coming up at this point. So we will not really spoil the ADC on any count. So this is the way generally a current transformer is used when you want to use it for sensing AC currents. Okay. Now, apart from this, there are other ways of sensing DC currents. So what we use for DC current sensing can very well be used for even AC current sensing, but vice versa is not true. What I mean is current transformer can be used only for AC current, but it cannot be used for DC current. Whereas the other methods, what we are going to discuss for DC current can be used for both AC as well as DC current. So the second method of sensing current is Hall effect sensor. So how does a Hall effect sensor work? So Hall effect is generally experienced by certain material. So if I am going to have a material like this, let me show it in 3 dimension. So if this is the Hall material that we are talking about, and let us say a current is flowing like this. This is going to be the current which I want to sense. Okay. And if I say that a magnetic field is applied with North Pole on one side and South Pole on the other side. At the top and bottom, I'm going to have the North Pole and South Pole. So North Pole is on the top and the South Pole is at the bottom. Okay. So this Hall material is placed in a magnetic field and it is carrying a current from, left to right. So this is carrying a current. So in that case, what is going to happen is because of the magnetic field that it is being subjected to, the electrons which are flowing here are going to get deflected in one way or the other. So they are going to get deflected like this. So you would see accumulation of electron on one side and depletion of electron on the other side. Because of the magnetic field and the material property of this Hall effect material, you are going to see that depletion of electron is on one side and accumulation of electron is on the other side. So this will create a potential difference. If I try to measure the potential difference between this side and this side, I will have, if I measure the potential difference, it is going to have some voltage difference in the form of millivolts or microvolts. So the Hall effect is essentially when a Hall material is subjected to a magnetic field and when it is carrying current, the charge carriers get kind of deflected, they get accumulated on one side and they get depleted on the other side, due to which there will be a potential difference existing between the two sides. So this potential difference will be proportional to the strength of the magnetic field to which it is subjected, and it is also proportional to the current. So I would be able to measure the current as well as the strength of the magnetic field. If I keep one of them as a constant, the other can be measured directly. But only problem is what we get is only of the order of millivolts. So the Hall effect output needs to be amplified further before it is passed on to an ADC. So this has to be done before it is passed on to an ADC. And depending upon if it is AC, then you are going to see continuously this potential difference also changes its direction. Something can be plus and something can be minus. So it will keep on alternating. Even alternating currents can be measured using Hall effect sensor. That's what I'm trying to convey. Okay. So what we do is we use a Hall effect material. In fact, Hall effect current sensors are directly available from LEM and so on. So for different ratings, they are available and they are built in with signal conditioning circuit. So you will have amplifier, level shifter, isolator, all those things. So LEM current sensors are available for various ratings. So they can measure up to 50 amperes, they can measure up to 100 amperes or several hundreds of ampere. And generally they come up along with signal conditioning and amplifying circuits also. So you should be able to directly connect the output to the ADC as long as you choose the correct sensor properly, and you might have to connect it to your power supply and certain resistor and so on. So all those things need to be done. So Hall effect sensors are one of those ways of measuring DC current. The third type of current sensing mechanism is non-inductive current shunt. So this non-inductive current shunt, you are going to use it basically to measure the current that is flowing already. It only thing is it should not really modify the current tremendously, but so it is like you are going to have this conductor carrying a current, and along with that you are going to connect a small resistance, and you are going to find out what is the voltage across this, and that can be passed on directly to measure what is the current actually flowing through this. So this will be actually I multiplied by whatever is this resistance that we are using. So this is going to be the voltage that is being measured, voltage that is being outputted by this particular non-inductive current shunt, and this can be directly, an index of what is the kind of current that this particular conductor is carrying. One problem is that you are not going to have any isolation. So sometimes we might use something like a linear optocoupler along with that. So the linear optocoupler essentially will take this input. So the optocoupler, as the name indicates, will have a coupling effect between the primary side and the secondary side with the help of light. So this is going to be an LED, and I'm going to have a phototransistor, and the phototransistor's output can be directly sensed to obtain what is the value that you have measured. So it will have a linear relationship. This phototransistor has to work in active region. So in which case, whatever is I multiplied by R, corresponding output will be observed here, and you should be able to directly say that the output of the optocoupler is proportional to whatever is the current that is being carried by the conductor. But only thing what you have to remember is that there is isolation now existing between the main conductor, that is the power, and the measuring circuit. So that is the major advantage. So in a non-inductive current shunt, you need to provide an isolation. So if you don't provide isolation, any fault that occurs on the power side can affect adversely the electronic side and vice versa. That is the reason why we need to have isolation. And the isolation is generally provided by a linear optocoupler. Okay. If we want to measure voltages or voltage sensing, if we want to do very similar to what we had used. So CT is for current sensing. AC current sensing, AC current sensing, whereas PT, potential transformer or voltage transformer, is going to be used for voltage sensing, AC voltage sensing. So AC voltage sensing can be done successfully by using voltage transformer. We said that CT should not be open circuited. It should always be connected with a small resistance. So a small secondary resistance is always necessary. This is what we said in the case of CT. The same way in PT, we should never, the potential transformer should never be short circuited. Because if you look at the PT, generally what happens is, if I want to measure the voltage from two terminals, across two terminals. So these are the terminals from which I want to measure the voltage. So this is the voltage to be measured. So let us say here I'm going to connect a potential transformer with n number of turns. And on the secondary side, I'm going to have only one turn. So this is going to be something like n:1. This is going to be the turns ratio. So this is the primary voltage which is being measured. And this is the secondary voltage which is coming up. So now Vs will be equal to Vp divided by n. So if there are n number of 1000 number of turns, and if this voltage is of the order of kilovolts, if I have the voltage of the order of kilovolts here, right, then I'm going to have actually this voltage, what I get will be kilovolts divided by 1000. So I will get it in the form of just volts. So, which is definitely handleable by any kind of ADC or any kind of electronic circuit. So, what we are going to do is to connect this voltage to an ADC, maybe after level shifting. So, I should say level shifter and ADC. So, I'm going to put a level shifter and ADC here, and this voltage is going to be given to this particular ADC for ultimately passing it on to my control unit. Okay, so this will go to the control unit. Okay, so we are going to see that a potential transformer can be used for measuring AC voltages, but I cannot use again the potential transformer for measuring DC voltages. So DC voltages have to be measured using a Hall effect voltage sensor. So Hall effect voltage sensor can be used for measuring DC voltages. So Hall effect voltage sensor should be connected to an optocoupler, and it should be connected to an amplifier, and then it should be fed to the ADC. So this is the way the voltage sensing will also work. Now, once we sense the current or sense the voltage, what kind of control algorithm we use, what kind of current controllers we use for making sure that the reference current is ultimately supplied by the power processing unit. So I'm going to discuss here three different types of current controllers. The first one is called current limit control. This is primarily used during starting or other transient operating conditions. So current limit control generally is going to have a particular value of current being outputted by the reference as the reference current by the control unit. So let us say, please recall what we talked about in case of the original control loop design. We said that if I want a particular reference speed, this will be compared with the actual speed, and what I get is the speed error, and this will be passed through a speed controller, and the speed controller output is going to set what is the torque reference, or it can also set sometimes current reference. So let us say it has set current reference in this particular case. So the current reference has now come up. Now, the current reference, especially during starting, for example, maybe I want to achieve 1000 RPM speed. This is going to be my reference speed. But I'm starting the motor drive, so the actual speed is going to be 0. So the error is going to be really, really high. This is going to be 1000 RPM. So if I say 1000 RPM is the speed, what I have got, I am really going to require a huge amount of torque to accelerate to 1000 RPM in a very short span of time. So normally the speed controller will also have something like a limiter. So invariably I will have until certain value of error, I may allow the torque reference to be generated in proportion to the speed error. But after that, it should saturate. Otherwise, the torque what I generate will be enormously high and the motor will not be able to really develop this. So this is essentially my delta omega or error in speed. And this is going to be what is the electromagnetic torque reference I am generating. So the electromagnetic torque reference, what I generate can be proportional to this omega, delta omega until certain value of omega. But after that, it will saturate. So this is probably the maximum value of torque that can be developed by my machine itself. It will not be able to develop more than this particular torque. So this is going to be TE max. Okay. Now, I have got TE max, or what is the current max in one sense. It can be TE max or I max. So I have put what is the I max. Now this I max is going to be fed to my current controller. So the current controller is going to look at this I max and then act accordingly so that my power processor will be able to generate this much of current. So in current limit control, what it does is I'm going to have what is the I reference. I have fed this. This may be I max. And I'm going to look at what is I actual. Okay. So I will have a comparator which is going to compare the actual current with that of the maximum current or what is safe for the power processing module as well as the motor to handle. So there will be a comparator which will be comparing these two. So if I actual is less than I max, it will not really interfere, no interference. Whereas if I actual is going to be greater than I max, immediately it will withdraw firing pulses. So it will not pass on the firing pulses anymore. So the comparator will take a corrective action in such a manner that it is actually going to, withdraw the pulses completely. So this is going to be the corrective action. So if by chance it sees that the current is greater than whatever is the maximum limit, immediately this is going to block the pulses. So there will be two options, either to continue with the functioning or block the pulses to the converter. So this is going to go to the converter and of course motor. So this is the converter and this is going to the motor. And motor is coupled to the load. This is coupled to the load. Okay. Now we are going to sense the current from here. So from here, the current is sensed. This is current sensing. And the actual current is passed down here. So this is the converter. This is the converter. So the comparator essentially takes action depending upon whether the actual current is well within the limit of safe current value or whether it is greater than the safe limit of the current. So correspondingly, it is going to either block the pulses from the to the converter or it is going to continue the functioning. So current limit control does not really allow the converter to pass a particular value of current. Rather than that, it is protecting the converter and motor against any accident that could happen due to high currents being passed through the motor and the converter. So the current limit control primarily is used during starting to get extremely good or quick response. So we will get excellent transient performance. So excellent dynamic performance. So current limit control is mainly used for this purpose, especially for dynamic operating conditions if I want to have a good performance from my control loop. The second type of current controller that is used is hysteresis current controller. So hysteresis current controller gets its name because this will allow an error margin of plus or minus delta I from I star. So if let us say I want to allow a current of 10 ampere. So I may allow either 9 ampere or I will allow 11 ampere. So I'm going to give a margin of plus or minus delta I. So how this works is somewhat like this. So let us say I have got a reference current as the output of the speed controller. So speed controller has given an output which is corresponding to I star. Okay. Now this I star is going to be passed through a hysteresis controller. And this is also going to get what is the actual current by sensing the actual current from the converter and the motor. Now, let us say this is going to be the reference current. So the reference current is somewhat like this. So this is the reference current. And with respect to time, I'm going to plot what is the actual current. So let us say I'm talking about the DC motor drive. And here is my DC supply. And this is going to be the switch, which is probably going to give the input to the DC motor drive. And here is the DC motor drive, which is receiving the current. And I am sensing the armature current from here. So let me show that I'm sensing the armature current from this point. So this is IA that I'm sensing. Okay. So this is going to be IA, what I'm sensing. So if I am having the switch S on, then I'm going to have an increase in current. Let us say I'm currently at this value of current. And when I am turning on the switch, the current is going to be pushed in by means of having the DC voltage source being connected to the motor. So I'm going to have increase in the current. Now the current has increased beyond whatever is the reference value. If the current has increased beyond the reference value, that is I plus delta I, it has even crossed this margin, then immediately the firing pulses to the switch are going to be withdrawn. Because it is withdrawn, now the motor current has to have an alternate path. So I'm going to have a diode probably connected, freewheeling diode connected like this. So a current will flow only through the diode. So slowly it will start dying down. Now it has died down and it has reached less than I minus delta I. The moment the current touches I minus delta I, immediately the switch will be turned on. So again it will increase. Then it will decrease again when once the switch is turned off after the current has crossed I plus delta I. So this is going to repeat itself. So if you look at the current waveform, this is going to be the actual IA. Whereas this dotted line, what I have got is the reference I. So the current will be actually oscillating between I plus delta I to I minus delta I. So depending upon what I set as delta I, what is the margin, current margin that can be tolerated, depending upon that, I'm going to have this current actually going back and forth between these two values. If I make this margin too small, very quickly it will turn on and turn off. So you may see that it is turning on and turning off very quickly like this. So hysteresis current controller will not work at a particular frequency of switching. It depends upon what is the sampling frequency of the current and what is the margin that can be tolerated, the error margin that can be tolerated. If you make the error margin too small, there could be very frequent switching, which we call as chattering. So chattering is basically extremely fast switching. That is generally not very good for the converter from two viewpoints. One is the switch itself can malfunction, And second is switching losses will be increasing tremendously. So it is not good to have chattering. If we have, so this happens when delta I is very small. The tolerance margin is very small. Whereas if I'm going to have a large delta I, then I'm going to have really, so current oscillations will be very high. Current oscillations can be high if delta I is large. So both are really not good for the hysteresis current controller loop. So we have to choose this delta I or the current margin judiciously. So to complete this control loop, what I have drawn, the hysteresis controller will actually pass on the control signals through a control circuit to the converter, and the converter is connected to the motor. So the motor is receiving its input signal from the converter, and the I actual is going to be fed here. So one thing is, this controller will always require a memory element because it should remember in what stage it is in, whether the switch is on or it is in off condition. If it is in on condition and if the error is within the margin, then it will continue to be on. If it is in off condition and if the error is still within the margin, it will continue to be off. So generally there is a requirement of memory element in the case of a hysteresis controller. This can be used even for an AC motor drive. In an AC motor drive, only difference will be you will have the current, what you require as the current, that is going to be a sinusoidal current in all probability. So this will be my I reference. So I may end up giving a margin somewhat like this. I may give I plus delta I as the margin for this particular current like this. The same way I minus delta I may give a margin somewhat like this. So I'm showing a margin somewhat like this. So if I am talking about a particular phase current for an AC motor drive, so I will normally drive an AC motor drive with the help of an inverter. So I'm going to have two switches of the inverter somewhat like this. So this positive switch will be connected to the positive terminal of the battery, and the negative switch is going to be connected to the negative terminal of the battery, and this will go to A phase or B phase or C phase. So let us say this is A phase winding to which this is connected. So the current that is flowing is going to be IA. So whenever I'm going to turn on Q1, at that point, the positive terminal of the battery is connected to the A-phase winding, because of which the current will increase. Whereas if I am connecting Q2 to the A-phase winding, because the negative terminal of the battery is connected to A-phase, the current will actually diminish, or it will go more towards negative direction. So I'm going to have Q1 on if IA has to increase, and Q2 should be on if IA has to decrease. So this is the way it is going to work. So let us say currently I am at some value somewhere here. And this value is actually, less than whatever is I star plus delta I. It is also within I star minus delta I. So if Q1 had been already on, so I'm going to have an increase in the current like this. Now I'm going to turn off Q1 once the current reaches I star plus delta I. Now once I turn off, it will come down. Then again, I will turn on Q1. Then I'll turn off Q1 and turn on Q2. So this is going to happen repeatedly like this. So I will have a waveform somewhat like this. This will be the actual IA. So the actual IA is going to adhere to the sinusoid, but with some error in the current, depending upon what is the kind of delta I tolerance I have fixed. So hysteresis current controller can also be used for AC motor drives without any difficulty. So this is one of the very common current controllers that are employed for various drive purpose as well as power electronic purpose. The third type of controller is called PWM current controller. So in PWM current controller, what is done is, again, whatever is your I star, the reference, that is compared with what is your I actual. Now what comes out as delta I, the error in the current, that is compared with a high frequency triangular wave or sawtooth wave. And that is going to decide how long your switch is going to be on or how long your switch is going to be off, especially when you are feeding a DC motor drive. We talked about the DC motor drive being fed by a single switch. This is the DC motor drive that is being fed by a single switch. So we can use, so here I'm going to use a comparator. And this output of this one is going to be the firing signal to the switch feeding the DC motor drive. So let us say I'm going to have an error somewhat like this. Okay, and I'm going to use a triangular wave. So let me just, or sawtooth wave. So let me show the sawtooth wave somewhat like this. So I'm going to have the sawtooth wave like this. Okay, so when I have the sawtooth wave somewhat like this, and this is the error in the current, whenever I'm going to have the sawtooth wave greater than the delta I value. So this is going to be the delta I value. This is the time. So I'm comparing the two. So whenever the sawtooth wave is greater than the actual value of current or the error value of current, I'm going to have the switch off and I'm going to have the switch on only during this portion. So I'm going to have it somewhat like this. So let us say this is Q is or S is on. So I'm going to say during this portion, S is maybe off and here S is on. And again, I'm going to have from here to here, S is off. So I am going to have the switch on and off adjusted depending upon what is the amplitude of this error. So if by chance I'm going to have an increase in the error after this, maybe there is a higher demand of torque. So I'm going to have an increase in the current like this. So I'm going to have the current error increasing like this. So if the current error is increasing like this, but I'm going with the same sawtooth waveform repeatedly, right? So here the current, the duration of the switch turning on is going to be smaller. So the current will decrease. So the error will decrease further. So you can adjust the turning on and turning off duration, how long the switch is on or how long the switch is off, that can be adjusted depending upon what is the kind of delta I am getting. So the delta I is going to indirectly determine how much is the current increase or current decrease, so that the error in the current can be bridged, the gap can be bridged. So PWM current controller is going to use basically a constant frequency sawtooth waveform or triangular waveform to ensure that the switching frequency is a constant here. So the switching frequency here is a constant, whereas in hysteresis current controller, you are going to have the switching frequency in this particular case is going to be varying. It is variable. It is not under your control. It depends upon how quickly the current rises or how quickly the current falls. Depending upon that, this kind of repeated turn on and turn off is going to happen. Okay, so the current controller, what we are talking about, depending upon your requirement, you may be employing a particular type of current controller for your application. So hysteresis current controller is very easy to implement, but the switching frequency is going to be variable. So it is not very easy to design a filter. If the switching frequency is variable, I'm going to have design of filter being more difficult. Design of filter is not easy. So I would say here designing a filter is not easy. Whereas in PWM controller, I know for sure the switching frequency is a constant. So whatever is present at the output voltage or output current, I know the frequencies which are present in output voltage and current are known. So we should be able to design the filter. So design a filter is simpler. In this particular case. Okay, so these are three different types of current controllers that are adopted very commonly in many of the drive system. So in the next class, we'll quickly take a look at PLL based control of an electric drive. Then we would go towards temperature rise calculation